Now that we have introduced the idea of molecules and compounds, let's take a look at how we actually express them on paper. One way that we do that is through formulas. Now there's two main types of formula. There's what's called the um, molecular formula, and then we have what's called the empirical formula. Okay, now both of these formulas give information about the elements that are involved in the compound, but they don't give the exact same information in terms of ratios. So the molecular formula is actually going to give us the exact number of atoms of each element in a compound. Whereas an empirical formula is only going to give us the whole number ratio of atoms of each element in the compound. Okay, so to give you an example of that, let's go back to a compound that I brought up previously, and that was water, H2O. Now, the molecular formula for water is going to be H2O. Okay, the empirical formula is also going to be H2O. Okay, and that's because a molecule of H2O contains the lowest whole number ratio of the atoms that are involved. Now let's compare that to something else like H2O2. Okay, hydrogen peroxide. Now if I were to look at a single molecule of hydrogen peroxide, what I would find is that there are two oxygen atoms stuck to two hydrogen atoms. Okay, so the molecular formula is H2O2. However, that's not the whole number ratio of the atoms of each element. There's a 1-to-1 ratio. So the empirical formula would be HO. Okay, another example would be something like glucose. Okay, glucose has the molecular formula of C6H12O6. But the empirical formula is going to be CH2O. Now you might be wondering, well, why do we even bother with having molecular formulas and empirical formulas? I mean, the molecular formula tells you exactly what's present in the molecule, and that's true. But we didn't always have the ability to figure out the molecular formula. Okay, so in the early days of chemistry, the best that you can come up with if you were testing a sample for the presence of different elements was the whole number ratio of elements. So based upon that, this is why we still look at empirical formulas. And you're going to see in the next chapter that we can actually derive the molecular formula from the empirical formula. So there's a lot of experimental ways to arrive at the empirical formula. And once we get there, the molecular formula is the next step. Now, in addition to the molecular and empirical formulas, we also have what's called the structural formula. And the structural formula gives us a lot more detail than even the molecular formula, because it actually shows us where the atoms are, well, where they are physically within the molecule. Okay, so for example, okay, we know that water is a combination of hydrogen and oxygen. We know that there's two hydrogens for every one oxygen. Okay, but the way that I've drawn this doesn't really give us any idea of how things are attached. The structural formula we'll use lines to indicate which atom is bound to which. Okay, and this can be very useful, especially when we start getting into more complicated compounds. But other examples of this would be something like, let's see here, CH4. Okay, or if we have something like, nope, wrong number there, hold on. If we have C2H6O, okay, there's actually a couple of different things that this could be. For example, it could be a compound like this. Okay, or it could be a compound that looks like this. And how would we know which one was which? Well, not by the chemical formula, that's for sure. You would have to have other ways of indicating it. And because these are organic molecules, this is actually a discussion that we'll have when we start talking about organic chemistry at the end of next semester. Okay, so this is how we deal with expressing molecular compounds. But there's another type of compound that we haven't talked about yet, and that's the ionic compound. Okay, and ionic compounds arise from the attraction of a cation, a positively charged ion, for an anion, a negatively charged ion. And the classic example of this, of course, is sodium plus chloride to give sodium chloride. Okay, but this is kind of tricky in terms of how to deal with how to represent sodium chloride. And that's because you never really have just one sodium and one chlorine. I mean, in the case of water, you could isolate a molecule of water, and if you look right at it, you would see one oxygen and two hydrogens. But sodium and chlorine don't just form distinct molecules. Instead, they actually form large lattices. Okay, so we describe that structure as a lattice. Okay, now if I were to represent the sodium with the color red and chloride with the color green, okay, what I'd find is that if I have one sodium get attached to one chlorine, which I'll indicate by this line here, even though there isn't quite this type of bond between the two, it shows the attraction between them. Well, there's nothing to stop that chlorine from getting stuck to another sodium, or for that sodium then in turn to get stuck to another chlorine. Okay, so you can imagine this extending out in that dimension. But by the same token, these two sodiums could find themselves stuck to chlorines as well. And these two chlorines could find themselves stuck to sodiums. And what do you know? We are already lined up for these guys to be attracted to one another. Okay, and again, this can go down in this direction. Okay, so we can see here is the formation of this complicated network of atoms, or I should say ions in this case. So even the smallest crystal of sodium chloride is going to contain millions upon billions of these interactions. So how do we, again, express this on paper? Well, we basically just treat it as if it was an empirical formula. So if I were to take that entire crystal of salt, okay, there might be one sodium attached to, 6 other chlorines, but overall in that entire block, there's going to be enough positives to balance out all the negatives, which means that we can say pretty confidently that for every one sodium, there's one chloride. Okay, so this becomes the way to express sodium chloride, but again, we have to remember that this is truly acting as an empirical formula. And I hesitate to say it should be taken with a grain of salt, because it's not truly a representation of what we have there. Okay, now, while we're on this topic, okay, you may have noticed that there are some chemicals that, well, some ionic compounds that have different numbers of atoms. So in other words, they're not always in a one-to-one ratio. So for example, if you were to consider the compound that would form from calcium and from chlorine. Okay. Now calcium is in group 2. Okay, and being a member of group 2, it takes on a positive 2 charge. Okay, chlorine is in group 17, and like every other element in group 17, it likes to take on a negative 1 charge, just like we saw in sodium chloride. But if I were to form a compound between calcium and chloride, I would need to make sure that my charges balance out. Okay, so what this means is I would need 2 chlorides for every 1 calcium. And what I would arrive at is CaCl2. Okay, now let's try something a little bit more complicated. Let's say we have a compound that's formed between sodium and oxygen. Okay, we know that oxygen is in group 16, and everything in group 16 likes to take on that negative 2 charge. Okay, sodium's in group 1. We know it likes to take on a positive charge. Okay, so in order to have enough sodiums to balance out that negative 2 charge, we need to have 2 sodiums for every 1 oxygen. So the formula that we wind up with is Na2O. Okay, we want to be able to predict what those ratios are going to be based upon the common charges that these elements take on. Okay, so another example would be a compound like magnesium, a compound made from magnesium and nitrogen. Now magnesium is in group 2, so it takes on that plus 2 charge, and nitrogen is in group 15, which means it's going to take on a negative 3 charge. Now this is a little bit trickier than the other examples, and that's because, well, we have 2 different values here. We don't just have something with a plus 1 or minus 1 charge, which is a little bit easier to deal with. Okay, so how do we deal with this? The easiest way is to simply take the number that's associated with the charge and cross it down to the other element. So the 3 gets crossed down to the magnesium, and the 2 gets crossed down to the nitrogen. And the answer that we wind up with is Mg3N2. Okay? So these are just a couple of examples, but it's expected that you will be able to look at a list of 2 elements and predict what their chemical formula is going to be based upon balancing out charges.